All right, well, welcome everyone. I am JJ. Let's do an example problem. We have an 8 kilogram mass here. M is supported as shown. Let's determine what our reactions in our fixed support here are at point A. I know I'm going to do equilibrium for that, so I need a free body diagram. So let's circle around this. I am trying to cut this away from whatever's holding it up. So if we cut through at A, I know I need to slice off that fixed support. As I come around, I'm going to cut the cable holding up the mass. And where we tend to struggle with this is, what do I do with this cable that goes off the top of my pulley? It's connecting back in to my beam. Can I close out this circle without cutting that cable? I can't. So I can actually just go straight over and finish this. If I dip down into that cable, if I cut it right here, for example, to get back, let's actually show this in a different color. If I came in and I cut that cable, if I dip down in here, I could cut the cable, but to finish my free body diagram circle, I have to come back up. Otherwise, I'm having to cut through the beam, and we can't do that. Cutting that cable twice, we'll get equal and opposite offsetting forces in here. It really doesn't do anything for us. Or I could just internalize, get that entire circle, or the entire cable up there inside my free body diagram circle. That's not going to show up. So I can just close out my circle in there. It's going to make my free body diagram a little bit more simple then. I know though if I'm doing that, I have a mass. For my free body diagram, I don't want to put in masses. I should put in weights. We sum up forces in here. My free body diagram should show forces, not masses. So let's convert that really quick. My weight should be my mass, 8 kilograms, times gravity, 9.81. Or this is going to be 78.5 newtons. 78.5 newtons. So that'll be the weight that I use for everything. From there, let's go ahead and come down below on this. So in my free body diagram, I'm going to start over here and just draw straight to the end of my beam. I know, let's go ahead and draw in that pulley that we have. I know at the end of the pulley, I have a weight hanging off of that. So I can show my tension going straight down, 78.5. I know my distance from A to the center of that pulley is 1,000 millimeters. And I know that from the center to the edge is the radius, 100 millimeters. I can combine that all together and just say this is 1,100 millimeters. From A to the far right edge of the pulley. I don't need anything coming off the top of this because it connects back into that nub of our beam. Or I could come in and say it kind of does this, comes in and connects like that. Either way, nothing's happening up here. I can just leave that off. The last things I need though are what's happening over here at A. For a fixed support, I should have an X component. So I'm putting in a X. I should have a Y component, a Y. And then the one people tend to forget all the time is fixed supports resist moment. I need an unknown moment, a couple moment in here. An M, A. We resist moment as well. So that has to show up in here for us to be able to work through this. But that's it for us. Let's come in and apply equilibrium. If I sum my forces up in the X direction, summing my forces in the X, I have AX, and that's it for us. Nothing else goes in the X direction. This equals 0. That's one of my answers. From there, I can sum forces in the Y direction. Summing forces in the Y. I have AY going up. Even though this equation is going to be easy, we're going to make the full equation and then solve it. AY acting up, our force from the weight coming down, minus 78.5 equals 0. Or AY is 78.5 newtons. We got a positive number out from our equilibrium equation, which means we got the right direction in here for AY in our free body diagram. We'll include that in our answer. It is going up. And that would be our second answer. We didn't put direction on AX because 0 is 0 in any direction. The direction kind of becomes irrelevant if we're 0. But my last piece, I need MA in here. To do that, I can sum moments up about any point I want to take a look at. I will sum my moments at point A with positive, going counterclockwise, summing my moments about point A. Right now, this doesn't have my variable in here yet. This is what equation am I setting up? I am summing moments at A. That will be my equilibrium equation. I can set this equal to, and the first thing I will put in is my variable, MA. That's what I'm going to solve for in here. Equals my couple moment, MA. AX and AY pass through A, so if we didn't know them, they wouldn't be included in here. Really, the only thing I need is this 78.5. It's going to cause a clockwise rotation, so minus force 78.5 times distance 1,100. And that'll get us to 0 in here. It's a super common mistake for people to leave this MA off. That has to be a variable in here. If we think of this just conceptually, if we ignore MA on that, our sum of our moments at A is negative 78.5 times 1,100. 78.5 times 1,100 is not 0. You have a mathematically pointless equation if you leave MA off of that. It has to be included in there. That is what we're solving for. Our sum is 0. MA is not. We can solve for MA, though. Our variable, we'll get a positive number out here, which means just like with our forces, we get a positive answer. We got the right direction in our free body diagram. MA works out to be 86,350 Newton millimeters. Or we could simplify that to 86.35 Newton meters. It's an equivalent answer. That's our magnitude, though. Let's get that rotation direction in there, counterclockwise. And that would be our final answer for us. Again, as we come in and do that, the key things in this problem, why I work it with my students, is people tend to forget to convert to mass, and they don't know what to do with a cable when it connects into the beam itself. And then reinforcing MA has to be a variable. Even though it looks like we're putting it in here, this is our equation term. This is what I'm actually solving for, MA. But we can get through these. We can tackle these. Keep working rigid body equilibrium problems. This is, in a nutshell, what statics boils down to, largely. Not entirely, but a huge chunk of our material is just building to this and then applying it in slightly different ways moving forward. This is really like the pinnacle, though, of where we go in statics. If this was useful for you, hit that like and subscribe button. Stick around. Let's get you an A with JJ.